First of all, thanks everyone for joining us today. I'm Jarvis. This is Ben, my colleague from DornerWorks. We're from Southwest Michigan. DornerWorks is a company that specializes in embedded systems and services. Is anybody else here from Michigan? Hey, great. Anybody else want to move to Michigan? We're hiring. We're looking for people with some expertise in Xen. So if you're interested, come talk with me or Ben afterwards. DornerWorks, we've been interested in Xen for about the last 5-6 years, looking how to apply it to the embedded space. Initially, we were looking at some opportunities in aerospace, but since then, we've really had a lot of interest in other areas like medical and automotive and industrial. Today, we've recently, in the last 4 or 5 months, we've collected some metrics, performance metrics on the Xilinx, new Xilinx part that came out late last year, and that's what we're going to be sharing today. Overview of the outline of the presentation. We're going to talk about we're going to go over an overview. We're going to talk about our motivation for doing this, to include like the metrics and the hardware target and tools. Then after we're done giving the overview, we're going to go through those metrics, talk about how we collected that data, and then share the results with it. And then we'll have a summary. We'll have a Q&A. So do recommend you save your questions until the end, because we have a lot that we'd like to get through in the next 20 minutes or so. Okay, first question is, why embedded Xen? Are there any embedded engineers in the room? Or most of you working with servers? I know the Xilinx guys are probably, but okay, we do have some embedded. All right. Okay, well that's good. Well, so the reason why embedded Xen is for a lot of the same reasons as we use Xen on servers. The ability to consolidate while retaining your logical isolation. It's also a way to manage your resources in a logical way that makes sense. Also, our customers are asking for it. I mentioned before we have a lot of interest from aerospace, auto, industrial, medical. And our customers are seeing it as a way to preserve their existing software architectures. So they're taking like legacy systems where they'll have single core processors, maybe running different kind of software stacks, and they see that Xen allows them to consolidate those all on one chip without having to port their applications around or change the underlying software stacks. Why performance metrics? Well, if you're going to add a software layer, customers are going to want to know the cost. Is it going to be memory space, latency, jitter, code size, overhead? They're going to want it. The customers are going to need to understand what the cost of adding Xen is going to have on their system. So which metrics? Well, some of the sort of rules of thumbs that we use to determine what kind of metrics we could collect would be metrics that would be useful for a customer, metrics that would be fairly easy to obtain, and metrics that would be unique to a virtualized system, something that isn't typical, you don't typically run into in an embedded system. So given those kind of rules of thumbs, what kind of ideas would you expect us to go with? What kind of metrics would you suggest? Crickets? Okay, well, what? Power consumption? Okay, that's not bad. Any others? Performance overhead, yep, that's a great one. Okay, well the ones that we focused on are boot time, interrupt latency, and context switch overhead. And the reason we picked these, so boot time is very critical in most embedded applications. That goes the time from power on to the time the device actually starts doing something. That also impacts reboot. If something happens, they have to come back pretty quickly. Interrupt latency in real-time systems is very critical. That will make or break you. If you had too much interrupt latency and you can't service your interrupts within a certain time, if you have a hard real-time application, that's a no-go. Interrupt latency, depending on your application, can also be a source of overhead, going to that overhead point. If your application services thousands or millions of interrupts per second, then the additional interrupt latency can be a big source of overhead. And finally, the context switch overhead. This is a new area of overhead for virtualized systems. In Linux, and other operating systems, you do have a context switch overhead. You have an OS overhead. This is an additional overhead on top of that the customers need to know about. Okay, so we're going to go talk a little bit about the new hardware that we have. This is the Xilinx Zynq UltraScale Plus MPSoC. Came out late last year, and as an embedded engineer, this chip is amazing to me. It has a pair of R5 processors. It has a GPU. It has an SMMU V2, and it has an FPGA, so you can do all sorts of fun stuff with this. But most importantly, it has a quad A53 cluster on there with a GIC V2 and 64 kilobytes of L1 cache and 1 megabyte of shared L2 cache. And it's used, it's currently being, we have our development board is the ZCU 102, again from Xilinx, with those A53s clocked at 1.1 gigahertz and the DDR4 clocked at 400 megahertz, and then a host of other peripherals if you're interested in doing development. Okay, so we'll go talk a little bit about the tools now.
Magic personnel switch. So I'm going to talk a bit about the tools that we were using for this testing and then go into some of the methodologies and then starting talk about some of our results. So who here is familiar with Xen-Trace and Xen-Elize, has actually used it, worked with it, not just know it's part of the Xen tools somewhere? Wrote it? It's a gorgeous piece of code. It makes me weep when I read the source code. So for people not familiar, very quickly, Xen-Trace is a real-time event capture system that's built into the Xen kernel. It lets you trigger different event types, capture timestamps, capture variables, parameters, whatever you want. It's like System Viewer if you ever used VxWorks. And it gives you this nice binary output that is really hard to read. So then we also have Xen-Elize. Xen-Elize takes the binary output, parses it, makes it a nice human-readable form so you can analyze your logs, afterwards see what happened, run your data. It's a very useful set of tools. So in its basic operation, each PCPU gets its own trace buffer that it logs trace events into. Xen-Trace then collects all of those individual trace buffers based on a trace event mask you give it, so you can tell it, look just for scheduler events, look just for IRQ events, look only for my special subset events that I invented just for this testing, and it will phase out everything else. Collects all of those, gives you a log. Then you send that into Xen-Elize. Xen-Elize does multiple various analyses on it. It can tell you scatter plots, it can tell you core usage, it can just raw dump out the log for you to look at. And then you can analyze and see what happened. So we use this a lot of times in our timing testing, in our latency testing to get data out of the Xen kernel. But there was a problem. Xen-Trace in current release Xen does not work on ARM. If you try and instantiate it, it will cause a page fault and fail. So the reason behind this is because when we switched from x86 to ARM and we switched to the new PVH memory map model, that broke the inherent memory mapping that Xen-Trace thought was going to happen. Because Xen-Trace sees DOM-ID Xen as a PV guest. And it tries to not perform address translation on it, which causes an explosion now with the new memory map model on ARM. So we had to fix that. And then also trace timestamp. Its timestamp wasn't built into the new ARM timestamp routines. And Xen-Elize simply was not being built for ARM. It was actually commented out in the makefile. So we made a patch. This was based on previous work by Pavlos Sukhov, if that's how you say his last name. I apologize. And basically what we had to do was we had to create a special case for the Xen domain, where if Xen-Trace tries to allocate pages, allocates memory for the Xen domain, we take a special case, we handle that translation separately, and then we allocate the pages separately, and return the memory back to Xen-Trace to get around the fact that its memory mapping isn't working correctly now on the ARM model. We then also implemented the TSC timestamp, so it's getting it straight from the hardware clock running at 100 megahertz for its timestamping routines. And we made Xen-Elize start building again. It works. We've submitted it into the mailing list for upstreaming. However, right now it's currently in review. And right now, it's being discussed by the developers if this is really the way we want to fix this. Because what we've done is we've created a special case for DOM ID Xen. That's separate from all of the memory mapping cases on the ARM platform now. DOM ID Xen is not auto-translated like every other domain now is. So it works, but the question becomes, do we really want to do this? We've created a one-off scenario. Would it be actually better to fundamentally re-architect the way DOM ID Xen is managed on ARM so it's not a special case? Make it an auto-translated domain, make it actually behave correctly on ARM, because the fear is we're going to get a lot of these single one-off fixes for it throughout the code. So we're working on that right now. It is in the mailing list, but we also have the patch available on our own local GitHub, if anyone really wants it. So now moving into our actual testing and results. This is the configuration we used. We've got the Xen Zynq Distro version 2016, Linux, and Xen 4.7, and we're running on our ZCU 102 testing board. So the first thing we conquered was boot time for Xen. So how long does Xen itself take to come up? We instrumented U-boot, and we instrumented the Xen kernel itself to place in timestamps that we could pull out of the system direct from the timestamp counter. And this is what we came up with. Over 404 samples, it usually takes around 876 milliseconds for Xen to complete its boot process. This, however, is contingent. It's mainly contingent about how much RAM you have. So if you increase your RAM, if you double your RAM to go from 2 gigabits to 4 gigabits, you get about 30% more time all of a sudden. So the page allocation, the page referencing, depending on your RAM size, will directly affect this quite a bit. Also, your DOM0 configuration. How much memory is it allocated? What resources does it need? All of those can slightly affect how long this boot time is going to be. But this was average based on our configuration with 2 gigabits of RAM. We then looked at the boot time for DOM0. So Xen is up. How long does it take for DOM0 to come up? In this case, DOM0 is the vanilla Linux DOM0 shipped with Pentalinux and XCD. We didn't change anything about it. So it's not optimized. All the print statements are there. All the initialization code is there. We didn't take anything out. And in this case, we instrumented it to go from the endpoint of Xen to the 2 different points, to the point where the actual Linux kernel init is done, and then the point where all of the subsequent init tasks then complete. And what we found was it takes about 5.13 seconds for DOM0 to boot. Quite a while. So down here, start point is the end of Xen boot. DOM0 actually physically starts about 35 milliseconds after that. This is the point at which DOM0's Linux kernel has completed its most primary base initialization, the point where we start the init processes. And then this is when we finally finish all the init processes and the kernel is fully up. So obviously this time frame in here is where a lot of optimization, a lot of configuration for your specific activity could be done to greatly reduce the time that this takes to boot. We then looked at interrupt latency. So on this platform, we have the GIC v2 interrupt controller. And what it does is an interrupt comes in, and it primarily gets delivered directly to Xen. Xen then looks at it and says, OK, is this interrupt for me? Is this interrupt for a guest? If it's for me, it just handles it directly. If the interrupt is for a guest, it then writes into a virtual GIC and decides if the guest is ready to receive the interrupt. If the guest isn't active, if the guest is busy, it will put it into a queue. If the guest is ready, it will trigger a flag in the virtual GIC, which will then deliver it to the guest. As far as the guest is concerned, it got it directly from the GIC. It has no idea it's been virtualized. It has no idea it's reading a virtual interface. So this is the process that we're looking at. And we were primarily interested to know, how long does this take? So this side is hardware. We can't speed it up. That's as fast as it goes. But then how much overhead does this entire Xen process then add to the interrupt handling that your user is then going to have to experience? So we tested this 2 different ways. First was we just plain timed it. So we put trace timestamps into the interrupt handling routines and measured how long the interrupts took to execute. And from that, we get about 2.35 microsecond overhead that Xen provides. So this isn't the entire interrupt processing time. This is just the amount of time that Xen itself contributes that would not be present in a native environment. And you see we get a couple outliers out here. Those happened when we got two IRQs at the same time, so they queued. So both were being processed by the time. Now, as a guest, you may or may not actually see that. If both are for you, you may see both of them come in. But if they're for different guests, you wouldn't actually experience that time delay. The second way we tested GPIO is based off a format global logic used, which was we used some GPIO. So we had one GPIO switch on the board, and we had a LED. And basically we said, OK, we hit the button, triggers an IRQ, triggers an interrupt. That interrupt triggers the LED. So hit the button, the light turns on. Hit the button, the light turns off. And by measuring with an oscilloscope the time difference between those two events, we could get a very good estimate of the interrupt latency. Right? So when we did that, we came up with these lovely charts. This is the native latency. So this is our test running with no Xen whatsoever directly on the hardware. Button gets pressed, LED turns on. And we came up with about 310 nanoseconds just for the native raw interrupt handling. Takes about 310 nanoseconds. We then did the same thing with the test running as a guest in Xen. And in that case, we came up with about 2.58 microseconds. So then if you take that, subtract out the native, you're then left with just the contribution of Xen, because we've canceled out now the native contribution. So that comes to about what we saw before, about 2.3 microseconds is the amount of interrupt latency that Xen itself is providing into the system.
OK. The next thing we looked at was some of that overhead from the context switching. So we did a few different configurations. We looked at the default credit scheduler, and we looked at the Xilinx 653 scheduler. And on both of them, we tried two different configurations where we put two domains on one core, in core 0, or we put in another configuration was we put the domains on their own cores, pinning them to the core. What we found for the credit scheduler is that even with both of the domains running on the same core, the expected overhead was quite low. Right, we're talking 0.04 of a percent. It's even better when we split them out and we run them on their own cores. Particularly DOM1, the guest that that the customer would be concerned about, is 0.008%. When we look at the Xilinx 653 scheduler, it's a bit worse. When we put the two domains on the same core, 0.1% approximately expected. But when we split them out onto their own cores, it gets a lot better. Now, little caveat, back up a slide. For the credit scheduler, we're using the default time slice of 30 milliseconds, and for the Xilinx 653, we're using a major frame of 200 milliseconds. So major frame, that's approximately that's how frequently the scheduler should run. So the question is, did we really, notice the weasel word of expected overhead? Just based on these measurements, we would expect to see a certain percentage of overhead. Now, we were wondering if that was actually going to be the case. So we ran another experiment where we developed an application that ran some dry stones, just to some dry stone benchmarks, just to exercise the CPU. We ran that natively to get a baseline number. And then we reran it as a guest with a number of different time slices. Obviously, the smaller the time slice, the more overhead we would expect, as there would be more scheduling and context switching potentially going on. So based on those results, we found out that no, we did not correctly measure all of the context switching. In fact, we were off by about a factor of 6. But what we did find was that for about 3 milliseconds, time slices and up, it was pretty constant. It was a factor of 6. So that tells us that, OK, we didn't measure all of the scheduler, all of the context switch correctly, but that is the major source of overhead in our system. And if once you get out here with the credit-based scheduler, after when you set a time slice of about 1,000 milliseconds, the difference between running natively and running as a guest practically disappears. I couldn't detect it. My results were the same with the sensitivity of my measurements. It's interesting to note that below 3 milliseconds, performance actually improves. Our overhead decreases. I'm guessing that there's a special mode in the scheduler when the time slice gets really small and goes into a polling mode or something.
Obviously, the math then assumes that it's larger than 10 milliseconds, and
Yeah.
doesn't work right when you're do less than that.
In the scheduler?
Yeah, so I think, yeah, anyway.
Yeah.
I think someone tried that and the math doesn't work right.
Okay. So, yeah, so that was, that's what we found with that. So even still, though, even with a factor of 6, we looked at the previous slide. The worst case we saw were two domains running on the same core on an airing scheduler. It was 0.1%, so that's 0.6%. That's still less than a percent. It's really marginal. So really, to summarize what we found then, looking at the implications with the boot time of with Xen 0.8 seconds and the domain 5.1, that really tells us we need to focus on optimizing that Linux, that DOM-O, to improve our times. And also by improving the Linux boot up time, we'll optimizing out drivers and things like that. That'll make some of our subsequent tasks easier as well, because there'll be less in there to have to analyze and determine the impact on the system. With an interrupt latency of about 2.3 microseconds, the question is, well, is that acceptable by a customer? We do have some embedded customers who that's acceptable to them. A commercial hypervisor claims to have an interrupt latency of about 2 microseconds. So we're on par with that. A 2011 VDC poll shows that less than 10% of embedded projects need an interrupt latency of less than 5 microseconds. So pretty strong indications that 2.3 microseconds will be acceptable to most customers. Additionally, 2.3 microseconds is a lot better than the 20 or 30 microseconds that were got out there, were being reported back in 2014. Some embedded customers, they found those old mailing lists and saw those numbers and were spooked. So they were very pleasantly surprised when we came back and told them about the 2.3. The context switch overhead, without doing much, it's already pretty negligible. And if you configure it correctly, you can get it down to approximately 0% with a large, pinning the guests to their own cores and giving large time slices, particularly in those cases where they're pinned to their own core. So future work, I've already talked about optimizing the DOM-O boot time. There are some things, we have some ideas about optimizing the Xen boot time. As Ben mentioned, the Xen boot time is highly dependent on the amount of RAM that's in use. It's like 30% of the time spent is setting up page tables, I think. The N boot allocator function, about 25% is spent on setting up the DOM-O itself, DOM-O create. So that's why I said before that optimizing our DOM0 will help with optimizing our Xen boot time as well. Our embedded customers, a very typical configuration is Linux in one domain and bare metal on 3 others, each of them pinned to their own core. So that's a very common configuration that we think we can provide some optimizations in the interrupt handling to speed that up for those cases as well. Obviously, go back and look at our traces to see where we're missing time to improve our estimate performances, and then get into measuring jitter and calculating worst case execution time. All right, at this point, we can ask some questions. Yes?
Do you have an idea, did you measure how long it takes if you're running guest mode just to go up into the hypervisor and straight back out again?
Yeah, make it to complete a hypercall, right. No, we haven't, but that was a great one to do.
And I know in the early, when I was doing performance stuff, in the early, on x86,
Yeah.
stuff, just if you do it, read the timestamp, and you do a null sort of thing out again.
Right.
Not processing in Xen, it would be on the order of a couple microseconds.
Right.
It's
I would expect it to be.
On also, Christopher that did some information map for that it was around 400 cycles on Xen, which on x86 is around thousands of cycles.
Yeah.
So
Yeah. So it's 400 cycles.
So for our typical customer, they're not interested in making hypercalls directly, right? So that sort of
That's going to limit how fast you can possibly make interrupt.
Right. Well, there's a lot more that goes in with the context switches other than just calling down into Xen in the first place. Making the hypercalls would be if there's a service they need from Xen itself, and for the most part, they want to pretend like Xen doesn't exist. They just want to use Xen to manage, keep things separated, and so they can throw 3 bare metals on and run their Linux as well, and have their cake and eat it too. So, but that's a good one to measure on this board.
But I mean, like, say if you're measuring interrupt latency, is it interrupt? You're switching from the guest into Xen and then back again, right? So even if Xen can magically be instantaneous,
Right, I see what you mean.
you would have
You need the context switch into Xen to handle the interrupt. So there's a little bit more, there's a little bit more time embedded. Yeah,
more hardware lower bound.
sure. Good point. Okay, thank you.
I'm curious about the interrupt latency.
Yeah.
This data, how many times you run the mining, is this the average value or is
It's an average value for the GPIO. That was a manual process, so we did it 40 times to get those averages. For the other one, based on the timers that we were running cyclic test in the guest, hammering it. I think we have. You did that one. Do you remember how many? Thousands. I think thousands of samples.
Thousands of times.
So that's a pretty good. On the left-hand side there, we have about 1,300 for the peak, and then,
this is the cyclic task.
what's that?
The cyclic task.
Yeah.
Yes.
This test is generating the interrupts, basically, for us to measure.
This is very impressive because, like, the Red Hat did the cyclic task on x86 and they show the maximum latency as 13.
So this is the latency in Xen that Xen would add, not the total latency that a Linux guest would see, because Linux itself is going to contribute quite a bit of latency as well, where it's handling then of the interrupt that's vectored to it.
Yes, you have that data?
No, we don't have that data.
That's then completely dependent on your guest OS, which is...
We're trying to abstract that so anyone can, decide on what they want. Edgar, you had a question?
Yes, so this test, I was going to ask the same about the maximum data. And this was running one guess.
Correct. Yes, Julian.
I've got a couple of questions. The first thing, can you go back on the previous slide here? No, the one with the example of putting the timers. What's prevent the processor to reordering the instructions? Like you're reading the timer, but the processor is free to move the instructions.
Say that again.
How to explain? So what you did is just you wait all system registers, but from the ARM point of view, it's not necessary that you will use the system registers and during the story, then doing the other instructions. The processor is free to reorder the instructions the way it wants.
You mean in the actual pipeline?
Yes. So you have like
Yeah.
a few cycles, a few microseconds that.
Sure. But that would be a minor, variation to it. I mean, how much would that account for, really?
It's really depends on the processor, but you can't.
That would be mine.
Yes.
Yeah, I couldn't.
But you still have because you work on microseconds, you may see a slightly difference.
So I mentioned before, like looking at the jitter, doing a jitter analysis. That's when we're going to start getting more deep into those kind of effects as well. So this was prior to this, we really didn't have anything. We had customers being like, can we even use Xen in our system? So this was the motivation for getting some of this data. But that's good. That's a good thing to take away. Thank you.
And I should mention, too, that in all these tests, the Xen trace itself, the trace calls do add an overhead. So there is some inherent overhead just from the use of even gathering the timestamps and all of the routines.
So second question, you mentioned about the Xen boot time is maybe quite longer sometimes.
Yeah, we didn't do anything special with it. We just did we used all the default behavior.
That's usually what takes a lot of time.
Yeah.
Because you have to go all through the memory and scrub.
Yep. Yep.
Page by page.
And at the moment, that's still sequential. So it's just single threaded.
Yes.
Right. So it's only one core doing it. The other cores haven't been fired up yet.
We see a difference when I'm booting on the models. It's like a really long time on the list where it's stuck scrubbing. So you may see difference with that.
Okay.
In our default setup, we do disable scrubbing.
Oh, do you?
So I think
Okay.
you might do too, actually.
Okay. Well, I'll have to take a look at that.
You can probably do it by default too, if you haven't taken it.
Okay. Yes.
How much is the board you have?
I'm sorry. So, what's that?
How much is this board?
How much is the board? Edgar was at about $5,000.
And I don't know,
Yeah. Yeah, the ZCU, I believe, right now has a price tag, I want to say about $5,000 or $5,500, but that's sort of like an early adopter fee too. I believe it's going to go down in the near future.
Yeah, because I asked someone like what's all $500.
Oh yeah, yeah. There are other boards. I do know there are other boards using the MPSoC coming out. Outfit called Ivea has designed a board and is shipping them as well. And we're actually DornerWorks will be porting the Xen Zynq distribution to it when that becomes available to us.
there's interest in getting boards for Xen development. Let me know and we'll see what we can do.
All right, where am I going backwards? Going forwards, okay.
Are you going to push these publicly anywhere? Like on blog or something?
Funny you mentioned that. So this presentation, it'll be pushed up to our forum, publicly available, this presentation. We do have, our Xen Zynq distribution is freely downloadable as well to use on this platform. Yeah, so we'll have all that information out there. Okay, any other questions?
Now, I don't know whether you saw some of the threads around testing the stuff where it's difficult to get hardware for. So I just wanted to remind you that, you should probably run whatever you do in terms of testing or release candidates for every release and then report back to the project such that we know it actually works on the hardware.
Okay.
Because right now, anything which isn't a server form factor, we can't basically automatically test.
Sure.
We've had, issues with a lot of the different development boards because we don't know whether people are testing stuff and releasing and then stuff might break. So it's
All right. Well, we work very closely with Xilinx, so we take so we kind of take what Xilinx has for their Xen. So they downstream from Xen project. We take what they have and then we downstream some stuff as well. So usually, if it works when Xilinx reports it works on a board, it'll work for us too. But
I want
yeah.
to make sure that in the release notes it says this, this release has been tested on this, and right now I can't do that.
Okay. So I contact you for that.
Pardon?
I contact you for that to let you know.
Yeah, well, actually, just we have test days, as I said, on a mailing list before we release,
Okay.
and then the release manager just.
We'll include that. All right. And then Xen, on the devel. Okay.
So on Xen Develop, there'll be there's a regular release kind of mail sent out like
Okay.
once a month or something.
Yeah, if
So
you
just
don't know
like-
that, 5-minute break, and I'll explain how the process works. We just set up a mail filter, mails rather than everything.
Yeah. Yeah. So I don't get 1,000 a week. Yeah.
I have a quick question.
Yeah.
So you mentioned like the calculate WCT as the future work. Do you have any idea how to calculate it?
How to calculate the
Worst case.
worst case execution timing? We have a lot of experience in the company from doing worst case execution timing analysis for some aviation 787 stuff we did. Actually, the lady who was in charge of it used to work at GE Aviation and is now works for DornerWorks. So we have experience doing that. I don't know the specifics off the top of my head.
So are you using like static analysis or you measure it?
It's going to, well, you can't measure, unless you can exercise the worst cases. Measuring it is if you measure just whatever, then you're going to get an average. You're not necessarily going to get the worst case. So you have to find out ways to force it into a worst case, and then the things and then there's analysis as well with it. So it's a combination of both. All the techniques, I'm not entirely up to date on all the techniques, but we have that experience in house, so that we're going to lean on.
Yeah, because the hardware you are using basically is not released. So
Yeah.
secondary model of the hardware and to calculate the
Right. Yeah. It does. It does involve a lot of modeling the hardware and figuring out what the worst case on the hardware is. So I'm not. I know some older architectures that had a non-deterministic, particularly when it came with I think cache lookups, something. So yeah. Yeah. So I don't know about this particular platform where the non-determinism comes in. All right. I think we're out of time.
So the last question
Oh.
about the class. So you mentioned that there was this discussion going on the main list. Last time, I remember it was like I think we already agree about something. So it seems to be your call to send the new versions on the Xen.
Did we come to an agreement?
I think so, yes. Stefan Ostabilli suggested an idea for the beginning, and we can go with that.
I'll have to relook at them. I didn't think we had come to an agreement yet.
Okay, if there is no agreement, I'm really happy to go further on the main list. Maybe go to that for that phase. So the video phase in 2 weeks now. But I don't think there was many things on your series.
Yeah, we were just on that last item. Everything else we pretty much could act except for just that last.
Yes, so it would be nice to have that for the next